So you're probably wondering, are you really going to build the Pied Piper thing from the Silicon Valley TV show? Because that's not even possible. And to that, I would say, well, we're not going to build that thing exactly. If you are familiar with the TV show, if I remember correctly, I think their product was a lossless compression algorithm, like for general purpose data, kind of like the Huffman algorithm or LZMA. I think those things are used in like zip files and 7-zip files and brrrrr files and things like that. This technique is kind of similar to those things, but it's actually kind of a new category of compression. I guess it's more kind of like a lossy compression. Maybe we'll call it generative compression. Anyway, and it's not for general purpose data. It's for images and videos, and it's optimized for specific domains of images and video, such as maybe video conferencing or basically everything on Pornhub. It might also be good for like, specific categories of video like cartoons, maybe like sports. This might be useful for like Cartoon Network or ESPN maybe. But I do think that this technique will probably generalize to other forms of video. Like if we had a data set that was like every video on YouTube, I think that it could do something there, but I'm not interested in low-hanging fruit of like incremental improvements. Like, ooh, look at this, I improved by like 1%. Like, I'm, you know, I understand why a lot of researchers are that way and why they have to be that way, but so in order to understand how, I'm going to introduce you to some important concepts, which if you're watching this, I assume you're probably already acquainted with these. But I'd like to arrange them in a way that I haven't seen anywhere else, and in a sort of simple way without like Greek symbols and needless jargon. If I mention anything that you haven't heard of or you don't quite understand, just search for it on YouTube, because literally everything has been done before and someone has made a video about it. So here's a quick rundown of the things that we're going to talk about. We're going to make sure that we understand the difference between scalable vector graphics and bitmap images. My buddy Gibson wants to know about image compression and how it relates to the transmission and storage of video. We're going to talk about lossless versus lossy data compression systems or algorithms, whatever you want to call them. We're going to talk about deep neural networks. Specifically, we're going to talk about generative adversarial networks, and how they're similar to autoencoders. And then we're going to talk about hashing algorithms and rainbow tables and how they relate to all this other crap too. So, though you've probably heard of most of these concepts, I think it'd be good to talk about them just to sort of pre-warm the assets, get them really loaded into your memory freshly. So, first off, it's a real easy one. we've got here is we're going to talk about bitmap images, which is here they've on Wikipedia they're calling it raster graphics. But basically, this is just like the simplest form of an image file. Like you can see here in the smiley face, which is, looks like this, but when it's blown up, you can really see the individual pixels. And like when you save this file or you transmit this file across the internet or a network of some kind, this like the format, what it looks like on the disk is it's literally like white pixel, white pixel, white pixel, white pixel, white pixel, white pixel, a million times, and then on the next row it's like white pixel, gray pixel, kind of dark yellowy pixel, and so on and so forth until it's finished the whole image. And these files can become huge because they are just not compressed. So another kind of file, which you're probably only really familiar with if you are like a graphic artist or whatever, the other sort of important graphics format is called scalable vector graphics, which is like really cool because wait, what was that? Okay, yeah, vector, like instead of storing a bitmap, which is just the individual pixels, you store like basically like a mathematical equation to like draw something. And why that's neat is that your computer can draw it in any size but maintain the sharpness. Like here you can see if this is a bitmap and we blew up this tiny little bit here, it would get all pixely like this because we're just making each pixel larger. But the vector has like a mathematical description of like these letters and all this stuff and can make it at any resolution. This Wikipedia example is pretty good, but I also brought my own custom example of this, which is open source. I'm going to put a link to the original author of this. So this is my Ubuntu Bionic Beaver wallpaper. This is a Linux operating system, and this is the mascot of this version, is this Bionic Beaver. And so here is that image in scalable vector graphics, which is actually this is what I used to make this one. And you can see it's huge, but because I have a 4K screen here, but it's also very sharp. And so, we can zoom in, we can blow this up, and we can just, I guess it won't let us go. This stupid program won't let us go past 2000%. But anyway, I can blow it up all the way, and these lines are still very sharp. This checkerboard thing means that it's got a transparent background, which, anyway. So here is the bitmap version of this file, which is a 4K bitmap. So this screen has as many pixels as 4 1080p monitors. It's massive, it's huge. So this file here is 31 million bytes. There's 31 million pixels in this image, and each and every single pixel is like explicitly addressed in this bitmap format file. The scalable vector graphic file has 2,354 bytes. That is like so much smaller because it doesn't need to address every pixel in the image. It just has like this formula that's like, okay, we're gonna make a circle like this, and then here's another circle. Actually, this image is like pretty ideal for this, for vector graphics. I don't know how like smart that algorithm is, but anyway, yeah, you get the idea. So now thing with these scalable vector graphics is that cameras can't really make them, and I don't know, you just gotta have like, I don't know how common the decoder is of this software on every device that people might look at your website with, or whatever it is. But cameras can't make these, and so cameras make bitmaps generally. I mean, I'm sure there's probably some experimental camera out there that like does this, or like something that tries. Anyway, so what cameras do is they make a bitmap, which, as we know, is a huge file. But there is hope. So here's that one. This is the bitmap. It's 31 megs. So here is the same 4K bitmap, but compressed with a format called portable network graphics. And it has reduced it down to this many bytes, which is much, much smaller. So here we are looking at the PNG version of the Bionic Beaver. And here you can see what I'm talking about. When I zoom way in on it, you can see the bitmap. Now the PNG format has reduced the size of this image by removing redundant pixels, like where all these pixels would be black. Instead of writing black pixel, black pixel, black pixel like 31 million times, it just says, okay, do a million black pixels and then do some yellow ones, and then over here is like a million more black pixels. And I don't really know exactly how it works, but that's essentially it. It just writes some instructions of how to fill in all this space so that we don't have to just write individually address each pixel. Now if we go here, okay, there's a bitmap. Okay, so this is the 1080 version, which is, this is also a bitmap, but this is just the smaller one, and you can see this effect is like, still the same thing here. Here's the scalable vector graphic, and we can zoom all the way in, and that line is still so sharp and crisp because, yeah. So, as I mentioned earlier, cameras create bitmaps. They don't create scalable vector graphics. Actually, the sensor inside your camera is basically just kind of like a screen where it's got all these pixels that display bitmaps, but instead of displaying things, it absorbs light in a grid, just like, anyway, it creates a bitmap. And as we know, bitmaps are huge. And, if you have a really expensive camera, I think you can have it saved to RAW, but pretty much all other cameras are going to do a compression to that data. So we saw PNG, which is what's called a lossless compression. So when you decompress it, you get the same exact bitmap as you put into it. And that's cool for a lot of reasons. But it doesn't make things as small as they could be. So we have lossy compression algorithms, which the idea behind those is that there is a certain amount of information in an image that if it could be removed in a clever way that nobody would notice, or the untrained eye won't notice. And another thing about JPEG is you can decide how aggressively you want to compress your images with this. So I have here an image which is from thispersondoesnotexist.com, which is really weird. This is a generative adversarial deep neural network that has been trained on faces, and every time you refresh this page, it generates a new face. And I'm going to explain how this works later on in this video or series or whatever. but you know, you can just sit here and do this all day. So anyway, here is an image that I have from there, and this is the original format that it showed up in. It's 1024 by 1024 images or pixels, and it's already compressed with JPEG. They didn't send me the bitmap because that would be a waste of network bandwidth and hard drive space. They sent it to me as a JPEG. I probably would have. I generally keep things as PNGs, but whatever. So this is the original quality, and what we're going to do here is we're going to, and I just by looking at it, I'd say that they probably, you know, use the highest quality level with JPEG, and it's a 1 megabyte file. So that I think that's right. So we're zooming in here. So I took this image and I ran it through my a program called the GIMP, which is like the open source version of like Photoshop or something. And I recompressed it, and I tried it on different settings. So I, with you know, the highest quality level of JPEG is probably just looks like this. So I didn't bother to do that one. But here is level 50 quality, and it's kind of, I don't really see hardly any difference. I can kind of see, you can sort of see these little lines here of squares, these little blocky things. I think they call them artifacts, but they're very subtle. They might exist in this one too, but I really don't see them in the original one. So this is at like 15% quality, like this one here. And this one is where you can really start to see the JPEG artifacts. I'm not exactly sure how this works, but you can totally see these like square things. And it's just getting real JPEG-y. This one is 1% quality, and it's just, you know, it doesn't even. A lot of information has been discarded here. But it is kind of interesting how it's gone and done this. These like circles and this like neat little gradient thing here, and it's just completely, it's like decided that this is just kind of gray. But it kind of, you can sort of gain an intuition of like what this algorithm is doing here. Like, what is this and those? These neat little sort of like pre-computed gradients that are probably stored in the decoder software, and yeah, like this hair up here is really kind of an abstract, some really abstract hair right there, and I like it. But you know, you zoom out like this, and you can still basically see that this is a face. You know, it's very sharp. What is amazing to me, you know, is that this is not a real photo of a face. This was generated by a deep neural network. A particular one called StyleGAN2. So I don't want to get super deep into what a neural network is or how it works, but basically, here is a super simple, ultra simple neural network, and the idea is that you have, on one side, you have your input neurons, which take as an input some number, and that's literally everything has to be a number. And then these neurons are connected to all the other neurons, and there's actually, see this thing they call the hidden layer here, there's many of these layers that are connected like this one. There are, you know, and each neuron is connected to every other neuron in the next layer. This is called a fully connected network, or sometimes called a dense network. And then eventually it comes to this output neuron, and that's your output. There is a particularly interesting architecture called an autoencoder, which is sort of pictured here. We've got our input layer, which So I don't want to go too deep into how deep neural networks work. But basically, it's a technique that's pretty new and is inspired by the way animal and human brains process information. Um, and yeah, basically, with neural networks, here is an example. This is an example of what's called an autoencoder, which I think is particularly interesting for our purpose, and is also happens to be like, a neural networks 101 sort of example. So in this example, with most pretty much any neural network, you've got on one side you've got your input neurons, which are pictured as these little circles here, and you've got your output neurons. And um, the idea with an autoencoder is that um, you want it's a very simple. You're putting something in over here on the input side, and you want to get the same thing out on the output side. And so I don't want to get super deep into how neural networks work, but they are a technique for processing information with computers that is inspired by the way neurons in an animal brain would do that. It's not exactly how they do it, but it's inspired by that. And yeah, so in a typical neural network, you've got your input neurons represented here, and you've got your output neurons, and then there will be. This is called a dense network. You've got inputs, outputs, and these hidden layers. In this one, there's only one, but you might have a number of hidden layers. That's where the name deep neural network comes from, because it's usually got many layers deep. This one is very shallow and has almost, like we'd use thousands of neurons, but here's a very simple one, for example. So, for example, you might put in these have to be numbers, right? So you might put in the values of the color values of pixels in an image, and then run it through several layers of neurons over here. And this has two output neurons, but this could be different. You might just have one output neuron, and it outputs, the probability of whether or not your input image was of the letter 4 or something, or number 4. Anyway, one of the problems in deep neural networks 101 class is classifying these numbers, right? So this is a data set. It's called MNIST, and it is a easily attainable data set that's been published, and it's got like 60,000 unique examples of handwritten digits from people. And so you'd get it, you get 60,000 little images, zeros, ones, twos, all, 0 through 9. And each one of them is labeled with what it is actually supposed to be. So all the sevens are labeled as sevens, and so on and so forth. So a common thing to do with these images in your deep learning 101 class is to train a certain kind of neural network called an autoencoder. And so here's a diagram of what an autoencoder might kind of look like. So you have your input neurons over here, which are just taking, you have one input neuron per pixel. And so here's a 2, and it's a 28 pixels by 28 pixels bitmap. And it's black and white. So it's just got, each pixel is just a number between 0 and 255 that is how dark is this pixel. And you just take those and put them into these neurons, of which there are 784 in the input layer. And those neurons are connected to this layer, just connected to this layer, and this one has 1,000 and 1,000. But we generally, in an autoencoder, we make it sort of hourglass shaped. This one is kind of hourglass shaped. There's a lot of different ways to shape this. But the important thing about the autoencoder is that somewhere in the middle, you've got this bottleneck, which it gives us our, later we'll call this our latent code. And then it goes back and, it's symmetrical. And so to train this autoencoder, this how the learning process actually works is, at the beginning, all of these neurons have randomly generated values. Like when this number from this gets sent to these neurons, each neuron like multiplies it by its weight and its activation. Wait, hold on. Each one of these neurons is connected to every single neuron in the next layer. And so this is incredibly computationally expensive, but you can still probably train this one on your old laptop pretty fast. How the training process basically works is like how this works mechanically, right? So, the value of this pixel gets put into this neuron. And each neuron has like two numbers, and it's the bias and the weight of that neuron. And all that happens is this number, so it starts in this one, and it gets sent to this one. Well, it actually gets sent to every single one of them. And then this operation goes, you multiply it by its bias, and then add the weight of that neuron. And then the same thing happens, with every other neuron, and then it goes through all these layers. And then, since these are all random, they all have random weights and biases, the first time you get through this, on the other side, this image is going to just be like TV static, from like, static. But what we do is we calculate how similar this image that we got is to the one that we put in. And then you do this process called backpropagation, where you calculate how far off the result was from what you wanted, and then you go backwards through the network and you adjust the weights and the biases. Maybe it's just the weights. I don't know, there's a lot of different experiments people are doing about this, but you go back and you adjust the value of these neurons a little bit, in the direction of what will get you closer to that result that you wanted. And then that's a process called gradient descent, I think. And then, anyway, I'm oversimplifying, but yeah. So the training process, you do this like with all 60,000 of these images, and you probably run the whole set through a bunch of times. And eventually what'll happen is you'll start to get an encoder that when you put in a digit on one side, it gives you the same digit on the other side. And I kind of had a hard time wrapping my head around this autoencoder thing, because I couldn't really see how this is useful for anything at all. Which I couldn't understand, because I'm thinking the output, you're just getting, the product of this is just what you put into it. And like, while that's a great metaphor for life, I don't understand how that's useful for the number 2 here. But I was just kind of looking in the wrong place, because the real product is actually this latent code here. So like, if this dense network here, if this middle layer was the same size as all these other layers, then for this network to generate the same image at the end, all it would really have to do is it would just have to learn to just forward the exact values straight across, like, and then just ignore all of the other information, and it would learn to do that really quickly. But by forcing it through this little bottleneck here, and actually I think it would probably perform better if this one was a little smaller. Like, these layers should get progressively smaller and then progressively bigger on the decoder side, but I'm sure this probably still works. Anyway, by forcing it through this bottleneck here, it means that the network has to like learn about patterns in the data set, and the data set is pictures of digits. So these, as you get progressively further through this network, which really, yeah, there should be more than 3 layers here. Each layer, like this first layer here, will probably learn patterns, right? So this is like a thing that recognizes patterns and patterns of patterns. And so these neurons, and it's kind of hard to wrap your head around, but like, given that all they're doing is just multiplying numbers and forwarding them, but they somehow encoded into these weights and biases becomes this knowledge of like, there's patterns here of like lines. Maybe it's learned a pattern of, okay, sometimes the line goes this way and sometimes it goes that way and sometimes it goes that way and sometimes there's a little curve. It learns little things, kind of like we saw when we zoomed way in on this thing. It learns little things like this, right? And it can then it can remove redundant information from this bitmap. It can just say, okay, well, we've got a couple of these little gradient things here and they're arranged like this, and the next layer can go, oh, well, if you've got a bunch of these little gradient patches like that, then we've probably got a 2. And so it can just put into this neuron, it can just put whatever, something that signals that, okay, we're looking at a 2. And then on this side, it's just kind of that whole process, but backwards. It's going, okay, we've got a 2. And so then this side has learned things like, okay, well, then we need to grab the appropriate little gradient patches, which I'm calling these little squares gradient patches. I just made that up. But, okay, so we're going to grab the right ones of those, and then we're going to arrange them some way, and then boom, here's your 2. Now, this is a vast oversimplification. I actually don't think that an autoencoder is even that smart, but somehow it figures out how to reproduce this too. So the interesting thing about this is that, like, if you say, for example, if you wanted to make a handwriting recognizer program, you could take each digit that a person has written and run it through this thing, and then you could look at the values that are in here and come up with some way of deciding, like, oh, it's got this sort of value, then, oh, that's a 2. We've just trained an encoder. Whoops. So the autoencoder's been around for a while, but this architecture, called the generative adversarial network, is fairly new. It was invented, well, it's attributed mostly to Ian Goodfellow in 2014. Although recently I saw somewhere that like somebody in the 80s like kind of proposed this, but we didn't really have the computing power or the data sets available for deep learning back then. Anyway, Ian invented this. Now, so I like to think that this is kind of like an autoencoder, except instead of your encoder and decoder, you've got your generator and your discriminator. And you can kind of see that it looks like an autoencoder that has been sliced in the middle and has been severed. And we have, whoever made this graphic has, swapped the sides. Why this is really powerful and interesting for computer vision tasks is what we're doing here is, so instead of the autoencoder, where with the autoencoder, you are giving it an image and you're just trying to get the same image out the end and hope that somewhere in the middle it has learned something about the image or the data set. It's learned something about all the images. It's found a common thread between all of these images. The generative adversarial network is interesting because you've severed, it's the same kind of shapes, right, but it's severed. And so in that space where the latent vector would be, and then the decoder would be crafting, we would get this input from the latent vector. And so the decoder would be crafting this image of a 2, or in this case, I guess it's flowers. In this network, this is called the latent vector. It's actually still called the latent vector, but some people will call it the input vector. And the input vector is just random numbers. And at first, when all of these weights of these neurons, of these layers, are set randomly, the image that it generates based on this random input vector is going to just be some noise. It's going to be some static right here. In this case, it'll be multicolored static. But then we have a separate network that we're training over here, which is taking it. This one is being trained on the images that the generator created and also the real images in your data set. So in this case, they've got flowers. And so we do the same process where we show it a picture of flowers, and it kind of compresses this, compresses the information. It tries to find some common thread, some patterns of patterns and patterns. And then over here at the output neuron, it says whether or not it thinks that this is a real picture of flowers. Or it might even say like a percentage of it. I think this is 100% a picture of flowers, although it's rarely 100%. It's like 99% sure this is flowers. And we do that same process of backpropagation with this one, where at first, because these are all random, you show it some flowers and it'll give you some random value for how real it thinks these flowers are. But we do backpropagation and we slowly correct these things until eventually it is a little bit better at deciding what real flowers look like. After showing it some real flowers, then we show it what the generator created, which at the beginning is going to be some random static, multicolored static, and we tell it, do you think that's real or not? And then we backpropagate through the network and correct the weights and biases until it learns that that is a fake image of flowers. It is not a real image of flowers, it's static, right? So this process goes back and forth billions of times. And as it goes on, as the discriminator learns some patterns about what, images of flowers, eventually the generator will probably do something like produce like kind of a colorful blob somewhere. And the generator, which is still in its infancy, is going, oh, okay, yeah, there's a colorful blobs. Yeah, that's more like it. And so then the generator will get a slightly better score from the discriminator, and the learning process is like started, and there's a literal learning curve, which, yeah, is pretty cool. Eventually, if everything goes the way it's supposed to, the generator will be able to produce realistic images of flowers, even though the generator has never seen a picture of flowers. And why this is interesting and more powerful than the autoencoder, because with your autoencoder you could generate pictures of flowers by changing the latent vector. If you trained it on flowers, you could change the latent vector and generate pictures of flowers, but it doesn't quite have as good of an understanding as this thing does, because this generator has like literally blindly felt its way to a place where it can create photographs of flowers. And so it has thoroughly explored every single possible thing that it could do to make a photo of flowers. And it's learned all of the different patterns of, like, okay, so like we have this certain color palette that we got to stick to. There's a general flower petal shape in there. There's certain little gradient patches that are probably common. Around the edges, if we just put blurry green stuff around the edges, it's learned that that just gets it a better score from the discriminator. Whereas what the autoencoder is doing is it's comparing, like, it's got this pixel for pixel cost function where it's like this pixel corresponds to this exact pixel over here, and given this input, it still wants a 2 that is written like that 2. So it doesn't have as much of an abstract understanding of what it's looking at as the generative network does. So here is the GitHub, the code repository for StyleGAN2, which was created by NVIDIA. And in this example, it's been trained on pictures of faces. NVIDIA has published this for free because this will only run on NVIDIA equipment, and I guess they're trying to sell equipment and make interesting stuff. So here's some examples of generated faces. So, and here, this is what I really wanted to show you. This is like the learning curve of the thing. At first, it's learning really fast. And then there's sort of diminishing returns, and you get this long tail here until at some point you have to decide that you're not going to let it train anymore. This particular one here, you can see that if you have one GPU, and this is like a several $1,000 GPU, not just a regular one. If you have one of them and you're trying to train it to this resolution, it's going to take like 69 days, almost an hour short of 70 days. If you have 8 of them, it takes 9 days. I mean, that's still a long time. So to give you an idea of how this works, so here, this persondoesnotexist.com, which is where we got that picture I showed you earlier. Anyway, what this website basically is this is, somebody has taken just the generator from StyleGAN2, as you can see, and every time you refresh this page, they're taking random numbers and putting it into this input vector here, and those random numbers filter through the, there's way more than 2 layers. They filter through all the layers, lighting up different neurons, and eventually this picture of a face comes out. So if I reload, here we get another one. And, StyleGAN 2 is much better than StyleGAN 1. it's on some of them you can definitely see weird little things. You can gain an intuition of things to look for that indicate that this isn't a real photo. Um, like this almost looks real until you look closely at it. Um, if you like, it's not zooming in. Okay, yeah, like this one, it's like, oh yeah, her headband hairpiece thing is kind of sparkly and that's cool, but then you look at it and it's like, that's like some weird alien nonsense there. It used to be there, you would see things occasionally like eyes that were different colors and like, different, you'd see an earring in this ear and a different one in that one or something like that. And then there was also these creepy things going on over here. Like, yeah, what? Yeah, Stallion 2 is way better. Um, oh, yeah. Nice. That is amazing. So, the last piece of the puzzle that really exists only as kind of a thing to help you understand what it is I'm trying to do with this deep neural video compressor, because that is what we're doing here. Another piece to this here puzzle is is a cryptographic hash function, which a cryptographic hash function is on a very simple level is basically an encoder. So, imagine that this decoder thing is gone, but we still have this output here. We've got our input and we've got our output. I actually have no idea how these cryptographic hash functions work. MD5 is a good one. But it's basically an encoder. So here's an example using text, but you could also use any file on your computer, be it an image or whatever. And here's our input, and here's the output, which in the case of hash functions, they call it a digest. And you run the word fox through this hash function, and you get this digest. It's kind of like a one-way encryption. So you can encrypt this, and you get this value, but if you have this value, you can't get this unless you have like a an Excel file where you've gone through and you've computed every possible combination of letters and their corresponding output. And then if you want to know what generated this output, you can go through that massive table of data and find, the matching one. That is how people crack hash functions. These hash functions are used to like store passwords encryptedly. So like when you go to a website and you put in your password, let's say your password is box, it generates this and compares it to the digest that is stored in the database, and if they're the same, then it knows that you've put in this password. And the output is always the same for a given input. Also, the output is always the same no matter how big the input is. So like here it's Fox and it's this size. Here it's like a whole sentence and it's this size. Oh, and another thing that this is trying to demonstrate here is like if you change one letter of this input, you'll notice that the output of these two, this letter, only one letter has been changed. The output is completely and drastically different. This uses some crazy fancy black magic math. It's not really important. I don't really understand it. I can't really explain it. But that's how that works. So this was kind of like part of my inspiration for this thing is that so there's a particular hash function called MD5, which people don't really use anymore because, well, it produces a hash that's like this big, right? And like if you read in here, it's talking about collision vulnerabilities and collision attacks. I was using MD5 to create digests for files in a data backup system that I was programming. And, this program would go through your computer and it would create an MD5 digest of every file. And then it would store that in a database somewhere. And then, the next day, it would compute this again, and if this has changed at all, then it knows that that file has changed, and so it knows that it needs to take the newest version of that file and upload it to the backup server. So this is sometimes people call this like a fingerprint. Take a fingerprint of the file every day, and then the other thing about this is like when you're retrieving files from the backup server, I could just go, okay, give me the file that matches this. And, because this is a unique thing, the odds of finding two files that generate the same fingerprint are like immensely impossible. But as files, as computers are getting more powerful, it actually is possible. It's getting easier to find two files that generate the same fingerprint. So with this particular MD5 hash function, because this is such a small fingerprint that it generates, compared to this much bigger one from SHA-1, which is another one, and these ones generate even larger fingerprints, but this one generates a small fingerprint. And so if you're using this to store passwords, which are actually generally smaller than this fingerprint, then it becomes really trivial for an attacker to generate a table of they could have a pre-computed database of every combination of letters and numbers or whatever, and their corresponding hash output, their fingerprints. And so then if that hacker wants to bust your password, they just have to get this hash and check it against the table. They call these rainbow tables. And here is a website that has rainbow tables that you can download. Here is an option. Okay, here's an MD5 rainbow table. It's got every character between every combination that is 1 to 7 characters in length, and it's 52 gigabytes. It's pretty big, like 1 to 10, and it's like 300 gigs. So yeah, it's not a trivial thing, but you could fit this on a USB stick, and this is how you can crack passwords. So for my backup program, I was thinking that MD5 is still perfectly fine for my use because I don't have so many files that I'm going to find collisions, which a collision is where you get two files that produce the same fingerprint. And this is a lot faster than the other algorithms. So I was like, I'll use this because also this isn't really a high security application, I guess. So I don't expect anyone to even be trying to find collisions. But I do think that it's really cool how this right here is basically essentially the identity of a file on my computer. or on my backup server anyway. And I can look up that file just by going, okay, give me the one that matches this fingerprint. So I got to thinking, like, what if I had, okay, so, this is 1 to 10 bytes and it's 300 gigs. So, um, you know, uh, this file is 1,000,000 bytes. So if we had a rainbow table with everything up to 1,000,000 bytes, I don't know how much data that would be, but it would just be an impossibly large amount of data. But just imagine, if you will, some infinite computer that can store a pre-computed table of every possible file that could exist. If you had this infinite rainbow table and you wanted to send this file to someone across the universe, and if they also have that infinite table, then you don't have to send all 1,000,000 bytes through your galactic internet connection. You just have to send this fingerprint and tell them to look up that file, right? So this is, in a way, it's like a compression encoder decoder, but I guess the issue with that is that the codec, the encoder decoder, that's what a codec is. The codec is impossibly large. Okay, so, but okay, there is actually, we're missing one thing from this theoretical system, which is that when the other person looks up the fingerprint, they're not going to find just this file, but they're actually going to find several files that match this fingerprint, right? Because you just can't encode that much information into this small thing. You're going to get a bunch of different files, but so with this, you'd have to send another small piece of information. Like maybe you send it, you send the number of bytes in the file, and perhaps, I mean, you could probably use another cryptographic hash function and just send or just the same one twice, and just send 2 fingerprints. Well, no, not the same one twice. You could send 2 fingerprints, one of MD5 and one of SHA-1, and that then the other person could narrow it down and find the file that from this infinite table. So at this point, you're probably getting bored and you're definitely not paying attention anymore. And you're at the very least, you're going, okay, Cameron, well, what the hell does this have to do with Pornhub? And I just have one more thing to really make sure that you understand what I'm getting at. So here we have our face generator. Well, in this case, it's a flower generator, but let's pretend that this is a face here. The same thing that generates, we put our random noise in here, and it picks out all these random features and generates this random face. So we'll take another tidbit from cybersecurity. Okay, so I'm going to explain to you quickly how the Face ID works in your iPhone, which I actually don't know. I'm sure that's a closely guarded secret, but here's how it basically works: is they have a generator network that has been trained on faces. It's probably actually been trained to, it's probably more sophisticated than this. It's probably looking for specific things about faces. But anyway, let's just say generates faces. It's exactly like this thing that's generating faces. But something we figured out how to do is how to actually run this backwards. So it's not a one, like this doesn't have to be a one-way thing. You could take a picture of a face and put it here and run it backwards through the network and get this random set of numbers that basically represents whatever face you put in there. Now, running it backwards is even more computationally intense than running it forwards, but you put a face in here and you get this random vector, this random set of numbers that represents that face. And so you get your iPhone, it takes a picture of you, it runs it backwards through this network, it gets this set of numbers, and it saves it somewhere on the phone. And then if someone else comes along, they look at the camera, it runs the picture of their face backwards through this network, it gets a vector, and it goes, okay, well that's not the same one, so I'm not unlocking the phone. So you get it, right? You come back to it again, you put your face in there, it takes a picture of you, runs it backwards, boom, you get a vector that is at least close enough to the one that is stored that it unlocks the phone. So it's not hard to imagine. I mean, I guess if you're still with me at this point, like, let's assume that this process can happen like 20 times a second, which it can't in this way, but there's ways of speeding it up. Anyway, you could use this to reduce the amount of bandwidth required to do a video chat. Like, let's say, let's do FaceTime. Instead of, because what FaceTime is doing is it's taking bitmap images, as we've seen. It's taking bitmap images, it's compressing them with something like JPEG, and then it's sending that through the internet to your phone or somebody's phone, you know, and each frame is like maybe only 54,000 bytes compressed, because it's probably compressed pretty hard like this. You'll notice, like, when your internet connection gets really slow, that it ups the compression to use less data so that it can continue to stream at the proper frame rate. But like this, okay, so this here vector, so the vector, this StyleGAN2 here, this right here, this image of this woman, or this imaginary face, when it's saved as a JPEG compressed image on my hard drive, it is 1,000,000 bytes. And it was created from this here vector, which this is the code for part of StyleGAN, which here you can see the latent size is 512, which another part of that is it's 4 by 4. So it's 4 by 4 by 512 bytes, basically, which I'm actually not certain that it's bytes. But it's, so anyway, essentially it's 8,192 bytes that are required. So you put 8,000 bytes in here, it filters through, and it comes out in this high resolution image that is 1,000,000 bytes. I don't know what that ratio is, but that's pretty good. So, you know, when your internet connection gets a little bit choppy and your phone starts like just doubling down on the JPEG and producing things like this, this image is still 30,000 bytes. Whereas this one could be produced using only 8,000 bytes. And so basically that's the essence of what I'm getting at. We can use this to compress images. Now, this one can only, it only knows faces. That's it. That's all it knows. We can retrain it on other things. You know, StyleGAN, there's examples of StyleGAN having been trained on these different data sets, like pictures of cats, pictures of cars, churches, horses, there's like bedrooms. You know, if you get on to the internet and you look up StyleGAN, if you go on YouTube and look up StyleGAN, you can find tons of like super trippy stuff that have been generated with StyleGAN. But if we, that's why I call this the application specific compression system. I think it would be neat to produce a proof of concept of this. I am missing something actually, because this right here, this generates still photos. And this is a still photo. Video is not a still photo. It is a lot of photos. But they all have, you know, there's a common thread in them. So it can, video compression algorithms are kind of like JPEG, where they actually do this JPEG thing, but then in the next frame, if nothing has changed in part of it, it just says, don't change this part of the picture. I mean, there's a lot of little tricks there that yeah. There's some good videos you could look up on how MPEG compression works, if you're curious. So for this video thing to work, we could just use this and just, I mean, because we're saving so much bandwidth that we don't really need to do those little tricks. But if we did it like this with no modification, I think it would work. It would just be, it would be wiggly, because the thing would have no temporal consistency. And I guess I'll have to show you what I mean by wiggly. So with no modifications whatsoever, if we just basically try to use our generator as an encoder to encode faces and then send that representation, that latent vector that represents the face across the network, and on the other end somebody decodes it and then they see your face, you know, just like that, I think it would work. As it's trying to do frames, you know, there's a few obstacles that we would have to overcome, which are totally doable. One is that whereas with the hash algorithm is always deterministic. So whatever you put in always gives you exactly the same output. With these neural network things, it kind of differs from thing to thing, but they're generally not always deterministic. I mean, this one would be frozen, but like, you know, if a person is talking, then in one frame their mouth would be in a certain position, and in another frame it would be in a different one, and that slight change in the vector might cause, you know, weird artifacts to appear, like a flickering of the lighting or something in the image. But that can be overcome. There is a lot of work recently. I mean, there's been tons and tons of work done on generative adversarial networks and the things you can do with them. But last year in particular, there was like, at one conference, there was like 20 different papers that were all had, that were in the topic of disentanglement, which is trying, what disentanglement generally has to do with, trying to figure out the numbers within this input vector, how to manipulate those numbers to get a different result in the output that you might want. So, for example, there is some work done on disentangling an object from its pose. So you could get, the vector for someone's face, and maybe at the beginning of your FaceTime call, you send the vector for your face across the network, but then you don't need to keep sending that. You could, after that, you could send the vector for the pose of your face. We call it a pose, but it's like has to do with like how your lips are posed and where your eyes are looking, and if your head is rotated this way or the other way. And so we get even further reductions in the amount of data that needs to be sent. As far as like, obviously in FaceTime, we're not just interested in looking at people's faces. We're often interested in looking at whatever they're looking at, or the scene around them, the background. And I mean, we could train, there's a lot of ways that we could solve for that. If all we did was just search for the faces and replace the face with its pose and other vector, I mean, let's see, in this frame, if you look at this frame here, my face is very small, so this is not going to save us a whole lot of data, but we could send the rest of this with JPEG and the face with this part, and we'd save some data. If we trained another generative adversarial network on common objects, common places, we could probably fill in the rest of this using a similar technique, which I'm going to tell you about next. And by next, I mean in the next video, because this one's gotten really long. I know that I was kind of stuttering and stammering. I only wrote half of the script, and the rest of it was I just made that, it was just freestyling there, and so it was a little difficult, but and I should really go back and redo it or edit it all out, but I'm just gonna be lazy, or maybe I'll just do this like iteratively, because I really actually am skeptical that anybody is going to watch this crap. So I'm just gonna slap together and post it. In the next episode, I'm gonna talk about using StyleGAN generators and encoders as a convolutional kernel for more general purpose uses, as well as how this could be used. I haven't really addressed how this would be used for storage, which would be really why this would be a killer app for Pornhub. We're also going to talk about upsampling, and maybe some like the deep learning super sampling that NVIDIA has created, because a side effect of this sort of technology is that if you had a really crappy image like this one, and you ran it through a properly trained encoder generator thing, which there's ways to train it to specifically know how to handle this. You can train it we can take images that are high quality, we can compress them down to this, and train it to know that this is supposed to look like that. And actually, just a byproduct of of training this thing and using it this way, it would upsample the images. So say, for example, okay, so if you were Pornhub and you have like vast video files on hard disks somewhere, and some of them are like low resolution um, shit that nobody probably ever accesses, but they have to keep it on a hard drive somewhere. So we could use this technique to reduce that file size like immensely. But then also when somebody wants to retrieve that video, it would automatically, as a side effect, it would produce a much higher quality image than was originally stored there. And the neat thing about that is that this model would never really have to, like, if it was just for storage, it would never really have to leave the Pornhub servers. Like, people wouldn't have to have this codec on their computers because the storage system could retrieve the latent vectors, generate this high quality video, and then stream it to you. So that's why I think that they should hire me at Pornhub. And uh, I would be a great guy for that position, for a lot of reasons, but I will explain in more detail in the next episode.